Okay, welcome. We're going to do the video 2 on logistic regression, and we're going to look at the logistic curve to help us with these probabilities. So this is really, to me, this is really kind of an interesting subject or interesting topic, because I was always interested in how you could predict whether teams would win or lose. And so, especially if you're a black and white thinker, these probabilities are quite beneficial. So let's kind of pick up. Again, we're looking at the Donner Party example, and we have it where you either survived or you died, and we have the data over here that helps us determine, well, what is it? Did age, was that a good predictor of whether you lived or died, or your sex? And maybe we could then predict other people with different ages to determine whether they lived or not. So we can't really fit a line to just leave it 2 points. We need to do something else. And so what we do is we want to find the probability that y equals 1 as a function of x. Okay, so we want, again, to find a family of curves that looks something like this, where y equals 1, where your x over here, and then x after some situation y is 0, or maybe the other way around. And so maybe we can kind of fit the curves, like connect them between them. So what we want to do is have different directions. We may want to decrease, or we may want to increase, or different horizontal locations. You know, maybe x should be 3 or x should be 500, and different steepness to kind of do that. So what we're going to do is use the odds ratio, the probability of success divided by the probability of failure. And the way we're going to adapt that is we're going to take the natural log of that. And what this tells us is that if we fit this natural log to this expression with a line, then we could get beta naught plus beta 1x. So in some sense, this is called this is the logistic regression model. And we fit not to the original data points, but we take the natural log of the probability of success over probability of failure and fit a line to it. So if you go on to the next page, at page 104, let's go ahead and solve the expression for the p of x. All right, so this is a little algebra. I'm going to shorten this p of x by p. So p over 1 minus p is going to be, or the natural log of that, is going to be equal to beta naught plus beta 1x. Well, to get rid of the natural log, you exponentiate. So you get p times 1 minus p equal to e beta naught plus beta 1x. Multiply both sides by 1 minus p, so we get e to the beta naught plus beta 1x plus p times e to the beta naught plus beta 1x. And then up here, get all the p's to one side. Actually, that should be a negative. And get to the p's to one side. And I'm going to go ahead and factor out the p there. So 1 plus e to the beta naught plus beta 1x is equal to e to the beta naught plus beta 1x, and just go ahead and solve for p, and what I get then is p of x is equal to e to the beta naught plus beta 1x divided by 1 plus e to the beta naught plus beta 1x. Now if you had Calculus 2, you might have seen this in the Hughes-Hamlet book, but this takes a look as that if beta 1 is positive, as x goes to infinity, this will go to infinity, this will swallow up, this will eventually become 1. And if you have beta 1 is negative, then as x goes to infinity, this goes to 0, the numerator goes to 0, and so you get 0. So let's go ahead and remind ourselves from Desmos what the various graphs look like. Remember that beta naught kind of tells us where it's crossing the x-axis and where sort of the horizontal slope is. If you kind of take a look at where it crosses 0.5, it kind of moves it across and kind of shifts it to the right a little bit. Beta 1 kind of tells us the direction and steepness. The higher it is in absolute value, the steeper it is, and when you get beta naught to actually be 0, you get a horizontal line. When it's positive, the slope is increasing, and if it's negative, the graph is decreasing. So beta naught affects You can say it affects the horizontal locations. And beta 1 is sort of in charge of direction, whether it's going increasing or decreasing, and steepness. Let's kind of figure out what x naught would produce 1/2. Well, if we could take this numerator to be 1, and the denominator, that would be 1 over 1 plus 1, or 1/2. So what we would need to solve for is that e to the beta naught plus beta 1x has to equal 1. Well, this must mean, because remember, e to the 0 is 1. So this would have to be 0. So x would have to be beta naught over beta 1 negative. And so that's a key value. If you plug this into this expression, beta 1 cancel off, you get minus beta naught, e to the beta is naught, e to the 0 is 1, 1 plus 1 is 2, or you get 1/2. And so one thing to note about this is that when you get to 1/2, that's where it changes concavity. If you look wherever it may be, where did my beta naught go? That's where it'll change concavity. Okay. So what is the tangent line slope to the graph of p of x at x naught? Well, we have to take the derivative. So the derivative of p of x, we've got to use the quotient rule. The denominator squared, beta naught plus beta 1x quantity squared, and then the denominator, 1 plus e to the beta naught plus beta 1x times the derivative of the numerator. So e to the function times the derivative of the function. Beta naught and beta 1 are parameters, so they're not varying, but x has a constant or a front of it, so we get beta 1. And then minus low d high minus ID low, all over the low squared we go, so to speak. So minus e the high, e to the beta naught plus beta 1x, and then we need to take the derivative of this denominator. Well, derivative of 1 is 0, and so we get e to the beta naught plus beta 1x times 1, or times beta 1. Okay, so now remember, when we plug in x equals to minus beta naught over beta 1, this makes this exponent 0, and e to the 0 is 1. So we get 1 plus e to the 0, e to the 0 beta 1 minus e to the 0, e to the 0 beta 1 all over 1 plus e to the 0 squared. Well, that's 1 plus 1 times beta 1 plus negative beta 1 all over and all my great calculations without y'all. And then this will be 2 squared, or 4, so you end up getting 1/4. So the slope there is always 1/4. So when the probability is 1/2, the rate of change is 1/4. Actually, 1/4 beta 1. Beta 1, you got to keep that beta 1, baby. So 1/4 beta 1. And so if depends if beta 1 is positive or negative and how steep the slope is at that point. So those are kind of key values. All right, now, so here's our step. We're going to use a new technique to estimate beta naught and beta 1, and that method is called maximum likelihood estimator. And the essence of the method is to solve for the equations beta naught and beta 1, which have the largest probability of generating the observed data. In other words, maximizing the problem. and competing choices would have a small probability. There's some really nice multivariable calculus numerical analysis, but we'll just have to pass and sigh and pass it by. So let's run logistic regression on the Donner part of data and write down the resulting model. So here's our Donner party data, and we're going to go to stat and regression, but now we're going to go down to binary logistic regression, because binary means two, either of a success or failure. Notice that there's also ordinal and nominal logistic regression, but we want binary logistic regression. We're going to fit the binary model. The response is whether we died or lived, and let's do status, and the response is that we survived. And the continuous predictor, let's go ahead and do age for the predictor. And so if we end up doing that, so we're trying to predict whether our age predicts whether we survived or not. We got the middle term, so we're okay. We don't have to have interaction terms. We hit OK. And what we find out is that 20 survived, 25 died. And what we get there is our regression line that y prime is equal to 1.819 minus 0.0665. All right, so just remember, this is not the probability of success. We have to plug it in to our expression to find out what the probability of success. So to estimate what the probability will be, we're going to have e to the 1.819 minus 0.0665x all over 1 plus e to the 1.819 minus 0.0665x. So we could graph this then to determine whether it looks reasonable or not. I'm going to use Desmos just because it's a little easier than trying it on the graphing calculator. But let's go ahead and change beta naught to 1.819. And let's go ahead and change beta 1, hate to give away my slider, but to minus 0.0665. Oh, I'm sorry, the beta naught should be positive. And minus 0.68. Well, okay, so it doesn't look so good, but that's because I don't have the scaling right. So I got to pull way back and kind of see what my graph might end up being. And the question is, does it look reasonable? So it looks like you have a worse chance of surviving the later you go, and really we only want to look between 0 and 1. So I think it's pretty reasonable to figure out the probability. So the graph looks pretty poor. And let's kind of zoom in and see if we can find out where it reached 0.5. And it looks about age 31 that it reached about 0.5. So we could graph this something like on our little chart here. 31, and this could be 1. And it could be very slowly decreasing. So I'm kind of exaggerating a little bit. All right. Now, we could just kind of predict here, and I think I will, just for kind of give me an idea of how we might survive. So I'm going to go ahead and type in the equation 1.819 plus negative 0.0665 times x divided by 1 plus the exponential of 1.819 minus 0.0665 times x. And just kind of see what we would get. Now here this case is x with some value that was left over. So I'm going to put my age in, or roughly my age. So I'm 55. I'm going to store that to x. And now I'm going to see what my probability of success of living is. My probability was only 13.7% chance of living. Not so good. Let's put your age in. Let's say you're 20 years old and you're out there on the Oregon Trail, freezing, trying to bundle up. And so let's see what you got if we're putting in 20 in for you. You have a probability of success of living at 62%. So you can kind of see that you might see some connection between the COVID virus as far as using logistic regression to determine what's the probability of surviving the virus. My probabilities go down because I'm a little older. Your probabilities are pretty strong, but doesn't necessarily mean that you will for sure live, because remember, the data could have been different. All right, so we're going to go ahead and start looking at inferences on the next video, and we'll take it from there. Bye.